Welcome everyone for this talk. I'll be talking about decision making with Mllib, Spark, and Spark streaming. My contact is my first name .k@samsung.com. So you can the first name the initial k at samsung.com if you want to contact. So here is a brief agenda for what we'll be doing today. We'll be mostly talking about decision-making systems and decision-making algorithms. So that's kind of is important thing to understand these algorithms, because that defines how we chose what are the components we chose and how we chose those components for the system. So Samsung SDS is a part of Samsung Group, is an enterprise solution arm of the Samsung Group, and it has a major footprint in Asia. It's a #1 IT services provider in Korea, and it has like 21,000 employees. But we, Samsung SDS Research America, are a small group who are focusing on part of analytics that we call advanced analytics, which deals with mostly decision making and recommendation. So we will be looking at some of the algorithms that we use, and also how these algorithms enable us to do distributed computing and also stream computing. I would like to acknowledge my team at the get-go. It's not just one person's work here, it's a lot of people involved in that as well. So we make decisions all the time. When we go to a store where we want to buy, we do make decisions. So we will look at how we make decisions, as well as what we do and how the algorithms make those decisions. So let's look at some of the examples of online decision making. In the ad world, you want to, in an ad selection problem, you want to show some ad, and you have a lot of ads to show from, and how do you make those decisions? That's one of the problem. And the other problem is, if you have a number of news articles and you want to show those news articles, how do you choose the news article to show? So website design could be thought of as a decision making problem. There are a bunch of buttons that you want to show with different colors. You can do A/B testing, and A/B testing in some sense is kind of trying to figure out, putting it in the wild and trying to figure out what works best. So that's also can be thought of as a decision-making problem. The other things could be which deal with money, could be real-time bidding, auction, and recommendation system in general can be thought of as a decision-making problem. So we'll be looking at some of these problems and algorithms that enable to do these kind of decisions in an online world. So before going into the details of the algorithms, and I'll try to be abstracting out of the mathematical things as much as possible, so that it's general and easier to understand. Before going into the algorithms, I'd like to have some of the terminologies in place. The action, or the arm that we call, is set of options that are available. If there are a bunch of ads that are available, that could be thought of as a bunch of actions that you can take. And the reward is anything from click or a sign up. If you're looking for sign up in an online world, that could be thought of as a decision or a reward that the system gets. And even the revenue could be thought of as that. Agent, as we call the agent, is the software system which is making these decisions. And the environment is the outside world. It could be either the online world where the user could be interacting with the system, or it could be an API that the agent is connecting to, where it's doing a real-time bidding. So that could be thought of as an environment. And the context is like the side information that is available for the decision to make. So we'll be looking at the general set of problems which we call learning from interaction. If you think of learning from interaction, there is the interaction that's happening, and then we are learning from it. So streaming kind of becomes an important aspect of these kind of decision-making problem. So there is, in all the decision-making problems, even when we make decision, there is this exploration-exploitation trade-off that we need to do. Should we go to a restaurant which I know the best or which I like the best, or should I want to try out new restaurant? So trying out new restaurant would be thought of as an exploration problem. So exploitation can be defined as making the best decision of all the information that you know from, and exploration is to try and going to gather more information. So we'll be looking at these kind of trade-offs. We humans do these kind of trade-offs in a way that we usually don't analyze. And in these algorithms, we will see how these exploration and exploitation is happening and how different algorithm approaches these differently. So there are some other examples that we can look at for the exploration exploitation. In an online advertising, as I told before, showing the most successful ad could be thought of as exploitation, and showing some new ad could be thought of as exploration. Similarly, restaurant selection problem, it could be trying out new restaurant as exploration and going to your favorite restaurant. And when you're trying to decide on a dish, you do the same. And similarly for the games, when you're making a move. Exploration exploitation is not something new for the subject of decision making. It's been there for a while. It's called differently in different areas. Risk taking and risk avoiding in economics, or investing in a stock that you're taking some kind of a risk. So that's kind of an exploration. And saving could be thought of as like exploiting what you know the best. Okay, I know for sure this money could stay with me. And similarly in marketing and in medicine, there is experimental treatments that you do that can be thought of as exploration. So okay, sorry for the formula, but it's not something scary. It's basically saying what is my expected long-term reward, and what we are trying to optimize is trying to maximize this quantity. So if I'm taking multiple decisions, initially I might take some decisions which are suboptimal, but over the time you will take decisions which are optimal, and then over the time you want to maximize your revenue or whatever reward that you are choosing. But when you do exploration and exploitation, there is a problem. When you initially are trying to explore, you might be taking some suboptimal decisions. So there is a regret. There is this concept called regret that we need to be taking care of. That is making if you knew that all the decisions at any given point of time, the best decision that you could have made at any given point of time, and what would be the reward that you got out of that, the cumulative reward that you got out of that, and what the algorithm is choosing, the actions that algorithms are choosing, and how much reward did you get. And the difference between the two can be thought of as a regret. If I had knew what was the best decision, I would have got all the money, or I would have made maximum reward. But because you are exploring and exploiting, in the initial phase you don't know what's happening, you incur a regret. And most of these algorithms that we'll be talking about will be trying to minimize this regret some way or the other. So the characteristics of learning that you need to understand from learning from interaction: agent is interacting with the external environment to gather more data, and agent's performance is based on its own decision. And the data available to the agent is based on the previous decisions. So if there is an ad which I haven't shown at all, I don't have enough data for that to make any decision out of. So you need to gather more information and for all these different options that you're going to show, and by doing that you collect information and then you make better decisions. So these are the type of algorithms that we'll be looking at. So let's look at one set of algorithms which is called the Multiarmed Bandit algorithms. I mean, imagine a casino setting where a gambler is in front of a slot machine where he has a lot of options to choose from, and each of the slot machine gives different payouts, right? And the gambler's dilemma is to either go and see which of the slot machine works best, or try to explore other options and see which one gives best. Let's say at the first pool he got some reward or got some money. he can either stick with it or he can go to some other options and see which one works best. Right? So there is this exploration exploitation dilemma that is quantified or is formalized here with the multi-armed bandit problem setting. So let's look at the problem settings. In general, there are k set of actions or options at every given point of time. Agent selects an action, environment gives a reward or no reward. In most of the gambling cases, probably you won't get any reward. But agent updates what it knows about each actions, and then it continues to interact with the environment. So how, at any given point of time, how does the agent makes these decisions? Right? So there are different algorithms to do. We'll look at few of them to this. So the simplest thing that to do is something called the Epsilon Greedy. Most of the time, I would take the best decision that I know of. Some of the time, like 10% of my time, let's say I take a random action. This is the simplest of the approaches, right? And so exploiting is nothing but choosing the one that gives you maximum reward. Exploring is just random choice. And it's the simplest of the approaches. Now we can deal with epsilon in a different ways. One is you can keep the epsilon constant. That means 10% of the time I will always explore. But from a regret point of view, you are taking a loss of 10% all the time. So you can then what you can do is you can maybe kind of decrease this percentage of exploration. Or you can do, okay, I will explore only for first few times, and then I'll look at all the data that I've gathered, and I will make the optimal decisions there onwards. But what Epsilon Greedy doesn't do is, if there are two options that are giving you close enough rewards, you end up making the one that gave you the better reward, you're choosing that most of the time, and you're ignoring the one that almost close to that as possible. So there are some problem with it. So what you could do is you could take action depending on the distribution of the reward, or depending on how the proportion of the reward that you got from. So that's the softmax approach, right? So at any given point of time, this scary looking formula will basically gives you the probability, and you at any given point of time. So this arm or this action would be chosen most of the time, and then next would be chosen this second best option, and then the last one would be this one. So depending on the proportion of the money or the reward or clicks that you are getting from the system, you take those actions appropriately. So what if the initial few explorations are not giving you reward? That means initially when you look at the proportion, let's say a few of the rewards you did not get any reward, then you might not choose that arm at all, or you might not take that arm action at all. So just looking at the average reward is not good enough. So the next one, which looks at the upper confidence bound, is dealing with that. So what it does is it just not looks at the mean of the reward, but it also looks at the confidence interval of the reward. So let's say when we talk about some money, we will say, okay, what would be the earnings? You would say, okay, it could be, let's say, $50 plus or minus 10. Or that plus or minus 10, that confidence interval is kind of used here, and then it takes an optimistic approach. I might get that mean reward plus the upper confidence bound, and whichever has the highest upper confidence bound, it takes that action. So the way it works is, when you look at this, when in the initial part of the time, when there is very little data for a particular action to take, the confidence interval will be high, because you are not sure about it. The confidence bound will be plus or minus, let's say, $50. So $50, $20 plus or minus $50, so it's $70. So it is being optimistic about that and says, okay, I will take the one that gives me the highest mean plus this bound. So this algorithm can be thought of as an algorithm which is looking at optimism under uncertainty. When it's not certain, it's trying to be optimistic. It's doing a plus on the bound. There are other approaches which I won't go into more detail, which looks at not just the mean of the mean and the bound, but it also looks at the whole distribution as such. So it looks at the whole distribution and then takes the decisions. Let's look at this from a streaming point of view. So initially when we take some decisions, we might take some random decisions, and we get some data for those. And what we do is we process those data. We update the statistics for each of these, like it could be mean, standard deviation, or those kind of statistics, and then use that updated arms to take next set of decisions, and you get next set of data for that. So you are continually learning about each of these options that are available for you, and you are keep on improving your model, and you are accumulating the reward for from a long-term point of view. So it fits really, really well. The multi-armed bandit setting fits really, really well for the stream processing, because you want to do stream processing because, let's say in the initial part when you're exploring, you want to, whatever data you got, you want to learn fast. Once you learn fast, you update your knowledge about those options, and then you take some more decisions. So it's a very good setting for stream processing. So these are some of the things that we might want to look at, like Epsilon Greedy is calculating a mean, estimating the mean reward, and Softmax is also estimating that and also calculating the Softmax function which we saw. And the upper confidence bond is estimating the mean and the confidence, and the Thompson sampling approach, which is kind of updating the parameters of the distribution every single time over the period of time. So we only looked at just action. This was the multi-armed bandit setting where you are taking an action, you are receiving a reward. But in the online world, there are a lot of other information that is available, like the context of the user who is logged in. Let's say a person logged in, you know maybe the location from the IP address, you have the time of the day, and you could have other information like the website that you are showing an ad on. That website might be of some e-commerce website, or it could be New York Times article which is a sports article. So you know a lot of this information that you are missing out when you are taking decision just based on multi-armed bandit. Multi-armed bandit is just trying to, given a set of option, it is trying to play each of these arms and then take the optimal decision over the longer period of time. So let's look at the contextual multi-armed bandit setting. At every time t, the environment is providing you with some kind of context. When user logs into your system or comes to your system, he is coming with some kind of information, like the location and those kind of things. So there is some context to each of these requests, and the agent chooses an action for that particular context. Now what we are looking at, we are not just looking at the one that gives you the maximum reward, but for that particular context. And the environment reacts with the reward, and then agent updates the model. So there is one more arrow here, which is the request that is coming in, and then with the request there is a context that is being generated here as well. So the goal is to take best action for that particular context. Now it becomes some kind of a recommendation problem, where a user comes in, you have bunch of actions, you have bunch of movies to show that you can list on the front page, and the movies could be customized to a particular individual depending on his previous taste and how he interacted with it, what he played, and things like that. So in each of these algorithms, now we have this information, the context, which is represented here by X, and the action that a particular person took, and the reward that it got, the action that we took as an agent took, and the reward that it generated. And what we are trying to figure out is a policy or a mapping from this context to action. I mean, it might look scary, but it's just saying that you are trying to find for every context, you are trying to find a mapping to an action. or set of actions. And here theta is the parameter of a model. If you come across some machine learning regression model, let's say a regression has a line, and the line has some weights like what is the intercept and what is the slope. So those kind of things are called the parameters of the model. And similarly, we do learn some kind of parameters for this model. And the parameters of the model, here is an interesting thing about this learning these parameters. The parameters of the model are learned by playing the data again and again and again and optimizing for that particular parameter. So if you look at the diagram here, and these are the two parameters that you are trying to learn, we will initialize these parameters at some random by initialization, and we look at the data, we look at this, and then try to optimize to given this, try to optimize for this reward. And we keep updating it over iteration, multiple iteration. And this is important in the sense that we are doing iterative jobs, and if there is huge amount of data, we want to pin that data in memory, and then we want to do iterative job. So most of this machine learning algorithm where there is a lot of iteration that's happening on the same set of data, and you are optimizing these parameters for those data. And this becomes a very good case for having some kind of a cached layer where you want to reuse the data again and again. So it's an iterative process on the data, and it's very great for in-memory. Let's look at, so some of these algorithms, let's look at how we do the batch as well as the streaming. Let's look at some of the streaming and what the streaming algorithm would give us. So the streaming algorithm, we start off with an initial set of parameters, and then we give at any point of time we get the data, and then we do quickly multiple iterations on the same data. When we do multiple iterations on the same data, we kind of optimize for this parameter, and we get one set of parameter. And then we do take some actions on those set of parameters. Using those set of parameters, all the new context will be served with this new model. And then we get new set of data, and we take the same old parameters and then try to optimize that parameter, and then so on and so forth. So it's a nice streaming approach where you get new information, and then you are trying to optimize for that new information that you got, and you keep on doing it. And there is a batch learning part of it as well. Okay, we can learn this iteratively in stream processing. Why do we need batch processing? If you look at it, the batch processing only looking at the data that has come in that particular time frame only. Let's say the users that are logging into your system are different in the morning and in the evening, or people in the morning, people who are going to commute, they're logging into system, they might be interested in something else, and in the evening, in the later part of the day, they might be interested in something else. So if you just optimize for that particular time, you might be diverging too much from the model. The model might go haywire if you keep oscillating like that. So, but I mean, of course, these algorithms have capabilities of handling that by putting some constraints, saying that, okay, don't move too much away from what I know before, only move slightly from that. But there is an important aspect that we are missing out when you are doing like this. When we look at all of the data, we might catch the long-term trends as well. Right? When you look at all the data together, we might have long-term trends that we can optimize on. So it is good to do batch learning in these kind of approaches where you are looking at long-term trends in this and then learn the models for that. So we can merge these two things. So let's look at that in the next slide. But what the streaming is providing is a fast learning and an approximate learning. And what batch layer is giving you is more accurate model, but it's also capturing some kind of long-term trends as well. So let's look at this from this timescale point of view. So how we do the batch learning and the streaming is at any given point of time, we iteratively optimize for the data that we received from that time frame, and after some time we collect the data for that time frame, and then we do a batch learning, and then swap the model, and then the new model at T4 starts from the model that we saw at B1, and then it keeps updating slightly, modifying that model, and keep going. And the other thing that you can also do is the old data might be stale. You don't want to look at data from like 5 years before. Maybe you don't have that much of seasonality that you want to look at 5 years of worth of data. Or depending on the problem, this time scale which you want to optimize on, which you want to look at the long-term trends on, might be different. So what you can do also is this sliding window that you can do, so that you are looking at only the fresh data even when you're doing batch processing. This one is optimizing for the latest data, and this one is optimizing for the batch data. So the algorithms that can do contextual multi-armed bandit are these algorithms, which I'm not going into details, but what this is, we saw the UCB approach, upper confidence bound approach, and this is kind of a linear regression plus, or logistic regression plus the UCB approach. And here is another one, which is the Thompson sampling versus using the logistic regression approach. These are fairly recent papers from Microsoft and Yahoo. Now let's look at the components of the decision making, and also look at the architecture from an overall point of view. So the software stack that we have had to do these few things. First is it had to make real-time decisions, and it had to be scalable system, because we are looking for a solution. We are as Samsung SDS, we are in a solution providing business, and we have to be flexible from the point of view of putting into Samsung as well as some other outside companies as well. So it had to be scalable, and it had to do both batch and online learning, both batch and stream processing. Kafka, which is, everyone uses Kafka. It's become the most important piece of most of the stream processing, where you have both stream and batch processing, where it has both producers and consumers, and it's distributed by design, which we wanted, and also it's fast and scalable. And the thing that we wanted also was this multi-subscriber, where you have the data coming into one particular topic. If you know Kafka, it's one particular channel, and then multiple consumers can extract from it. So you can do one streaming job, could do some statistics on how many messages you are getting, and the other one can do online learning, and other one could archive the whole data into the HDFS. So that was an important piece for us, and of course it's persistent messages. The other important piece from our architecture point of view was Spark and Spark streaming. It's a high volume. You can do feature extraction, and you can persist the RDD in memory, and then you can do iterative jobs on it, and you can train models from historical data, and also you can use the stream processing, the Spark streaming in the stream processing. And the important thing for us was the machine learning library. You can build some algorithm, and you can, with some slight modification, you can run both on batch as well as streaming. So from a machine learning, from an algorithm or model parameter fitting point of view, you don't have to modify too much, and you can run the same thing on both the system. So machine learning, as I said, it was the most important factor for us. It's a very good integration with Spark, and it has a lot of distributed algorithms. There are a bunch of distributed algorithms. I mean, the most important thing for us was the optimization algorithm, where we had written our own algorithm on top of it, because most of the decision-making algorithms are not there in Spark. So we had to write algorithms on top of it, and we use the optimization algorithms that are there. And also it has a very good community. It's a growing community. We are also contributing to this, so it's in the pipeline of contributions that it has to go into the system. So the model storage, we use HBase. The model storage, we use some NoSQL, one of the NoSQL HBase database, but the architecture is written such a way that depending on the solution that we need to provide, we can switch that and put any other NoSQL or any other database. And the models are stored in PMML format, which is the predictive model markup language. It's the XML format which can be imported and exported out of the system. So let's say a data scientist want to code or build a model in Python or R. He could do that and export that model in this format, and then we could use that in our live system. So it has this capability, so we keep that in that particular format. And we also store for all the models and metrics in this store, because whenever we build model, we can build multiple of these models and then try it out in the wild as well, how each of these models are doing, A/B test those models. And an important thing to do then is to keep all the statistics of how it is performing. So this is the Lambda architecture that we have. Of course, there are some of the missing pieces. I only put the important pieces in here. The Kafka is the message bus. There's a speed layer, there's a batch layer, and there's a serving layer. We'll look a little more detail into each of these. The serving layer is where you get request. It's a play framework. It is the interface. It is the one which is interfacing with the external world. It could be a software system, because we as the analytics framework, we don't deal with customer and all those kind of things. So there is another system that can come in front of it, and all we deal with is the request, response, and actions and reward. Only those kind of things. And it's low latency, and there is a mechanism to have multiple models and A/B test those models as well. So those kind of capabilities are in there. And we process request, reward, and retrieves, caches it, and logs all these messages into Kafka. And that once it logs all these messages into Kafka, a stream processing, which is doing an online learning, could make use of that. So the speed layer, which is taking these messages from the Kafka, updating these models, getting the new model. So there had to be an arrow here which is missing. It's an arrow on both ways. It gets the model and then updates the model with this new batch and then stores it back. So it's a Spark streaming application, receives message and notifies the serving layer saying that, okay, I have updated the new model. You probably want to use that new model to give new actions or new recommendations, depending on the application. We also have a history logger, which logs all this data from Kafka into HDFS for long-term purposes, depending on how frequently you are running this batch process. You want to store this for a longer time. So it's also a Spark streaming application. It stores things in HDFS. And this batch layer gets this data which is stored in Hadoop file system, runs these algorithms that we talked about, and then it runs over a longer period of time as well, because it's trying to optimize better. And because it's a Spark job, you can pin these distributed data sets, which is called RDD, and pin them and then do iteration on top of it. So we also have this we can configure, as we looked at in the previous slides. We can also do this sliding window of how much you want to use for building these models. And the important thing to note is it builds the model from scratch, so that it looks at the whole data. I mean, for some of the models, you can start off with the parameters so that you can optimize faster, but sometimes it works best if you are doing it from scratch. So there are other management services that I won't delve into details, but there are other services that are available from the framework, analytics framework point of view. And the other important thing is scheduling all these workflows. We have written our own. We looked at a lot of workflows, schedulers, but we had to customize a lot, so we thought, okay, we'll write our own. This is another look again at the whole of the architecture. So make a quick recap what all we looked at. We looked at decision-making algorithms, and we looked at exploration and exploitation trade-offs. And we looked at how this exploration and exploitation, when we explore, we have a lot of information. We want to process it faster, and stream processing helps in those processing things faster and then update those models. We looked at two classes of algorithms, Multiarmed Bandit and contextual Multiarmed Bandits. There are other algorithms which I haven't talked about, but to keep the talk simple, I took these two. And it's been used, this contextual Multiarmed Bandit is being used a lot of places for ad placement, LinkedIn, Yahoo, all those guys use these kind of algorithms as well. And the need for, we also looked at the need for stream processing and batch processing from the accuracy point of view, and also how fast you learn from that point of view. And we looked at Lambda architecture, how Lambda architecture kind of helps us to do these two things. Okay, so now I'll open it for any questions. So the question was how much data is needed for batch processing versus how much data is needed for online stream processing. I mean, that depends on the problem that you're looking at because it depends on the seasonality aspect of it, how much data you want to use to kind of optimize on. So it is problem specific. Let's say you have ad. If the ads, let's say the ads that you have used, like historically, it might not have value because the ads keep changing. Or if you look at news articles, right? If your news articles, you don't want to learn this way too far away, right? Because the news keeps changing all the time, and you have to be really, really fast and adapting to this recent changes, recent trends. If some news is picking up, you want to show that more. So it depends on the application. So yeah, it depends. Most of the machine learning, when people ask the question, the answer is mostly it depends on the application and the problem. Yes?
In the sliding window, when you have like a batch and it's kind of moving, I guess you don't process the entire batch again when you have like a oldest event from all news being added.
Yes.
So how do you subtract the results of the oldest events while adding the results of the newest event?
Because we store things in HDFS, you can store it in a way such that it's date and time formatted so that you can kind of make a blob of the folder structure and then use that as a batch, as a moving window. So,
but you do recalculate for the whole batch again?
Yes, okay. Yes. We do recalculate because some of the metrics that you want to look at the whole data, and then so you want to probably get the whole data and then calculate it. So yeah. Yes. Okay. If there is no question, I'm available today and tomorrow as well. So if you have any question about using this solution, because we are in a solution provider business, or you want to talk more about the algorithms or anything else, I'm available. Thank you. Thank you.